code TN158TZ.
In the Gloucestershire countryside, not far from Cheltenham, there's an important research establishment where scientists develop uses for a most valuable raw material, coal. This is CRE, the Coal Research Establishment, run by British Coal. In this film, we look at just some of the work done here. But let's start with a simple experiment in the school lab. If you distill coal, you get a number of products. Coal is a complex mixture of substances, mainly containing carbon, and heating it breaks them up in complicated ways. Tar, coal tar, is produced, itself a mixture of many carbon compounds. And an inflammable gas is given off, coal gas, which used to be one of our main fuels in industry and in the home. Here's the coal tar, which has condensed out. This used to be an important source of industrial chemicals and still has many uses, particularly in the building and construction industries. When the distillation is complete, coke is left behind. This is more porous and brittle, but harder than the coal we started with, and it's a very important industrial raw material. In the school laboratory, you can easily make coke on a very small scale using a test tube and Bunsen burner. At CRE, where they do a lot of work on coke, they make it on a rather bigger scale in a small version of an industrial coke oven. Here's some finely divided coal ready to go into the coke oven. It's loaded into the top of the oven. This experimental oven is heated by electrical elements built into its side walls. Industrially, the gas made from the coal is used to heat the oven. The gases and tar vapors produced are burnt off. It's an experimental oven, and the temperatures and pressures built up inside can be monitored as the coal turns into coke. After 18 hours, with the temperature at 1050 degrees C, the coking process is complete, and the oven can be opened up. The coke is taken away to be cooled with water. They turn different blends of coal into coke in order to test the quality of the different cokes produced. The coke produced from a given sample of coal is graded, sorted into different sized lumps. It's important to see how much you get of different sizes, because only certain size lumps are suitable for use in, say, the blast furnace for iron production. It's also most important to know how strong the pieces of coke are. They mustn't crush to powder in the blast furnaces, which would stop the flow of gases in the furnace. One way of testing the strength is by seeing what happens when lumps of each different size are rotated in a cylinder with baffles inside, which fling the coke around. If the coke's very brittle, this will smash it up into smaller fragments. After a set time, they sieve the pieces to discover what sizes the coke has broken down into. By coking different blends of coal, examining the coke produced and seeing what its mechanical strength is like, CRE scientists help the coal industry produce the right kinds of coke for many industrial uses, and especially for iron and steel production. What they discover can be applied in the huge coke ovens, such as these, which supply industry with this vital raw material. After the coke has been discharged, it's quenched with water, just as in the laboratory procedure. So, when coal is distilled, it's called carbonizing the coal, many products, including a lot of tar, are produced. Coke is left. It's possible to carbonize coal under different conditions to produce smokeless fuels for use in the home, like this one. When a smokeless fuel is heated, it produces much less tar than coal does, as you can see. At the CRE, another of the jobs they do is to test smokeless fuels to make sure that they behave as they should do when they're burnt in domestic fireplaces. This is an ordinary grate, but the fire guard carries heat detectors to check that the fuel is burning correctly and giving out the heat it's supposed to. An electrostatic precipitator like this one is used to collect the tiny amount of smoke going up the chimney. Each channel has a wire running down inside it, to which a high electrical potential is applied, so that there's a voltage drop between each wire and its metal channel. This causes the tiny smoke particles to become charged themselves, and they're attracted to the metal casing, where they stick. For a test, a clean precipitator is first weighed. It's fixed in position at the top of the flue above the fireplace. A very high voltage is used, and for safety it can only be switched on using a key, which itself can only be pulled out when this door is closed. The electrostatic precipitator will now collect any tiny particles of smoke coming up the chimney. No smokeless fuel is completely smokeless, but there mustn't be more than a certain very small amount of smoke. The test runs for several hours, then the current is switched off and the precipitator is taken away and weighed again to make sure that the fuel isn't producing more smoke than it's supposed to. They don't only test the fuels made from coal at the CRE, they also carry out experiments on different kinds of grates and stoves to see how efficiently they work. Here's a setup to see how much waste heat goes up the chimney, not only from the fire itself, but also because some of the combustible gases produced may escape up the chimney without burning. The gases going up the flue can be piped off and analysed chemically using this equipment. The chemist measures the rate of flow of the mixture of gases. Any water vapour and carbon dioxide in the gases is absorbed in these glass vessels, and their increase in mass shows how much there is of each. Inside here, there's a glass tube containing copper-2 oxide, heated to 425 degrees C. Carbon monoxide present in the flue gases is oxidized to carbon dioxide. And any hydrogen present is turned into water vapour. The new CO2 and H2O coming out here are then absorbed in these vessels, and the increase in mass tells us how much CO and H2 there must have been. The gases now pass through another length of combustion tube containing copper-2 oxide, heated to a higher temperature, 800 degrees C. Here, any methane, CH4, is oxidized to carbon dioxide and water vapour. The CO2 and water vapour from the methane are now absorbed and weighed, so we can work out how much methane was going to waste up the chimney. CRE scientists and technologists also design new equipment for burning solid fuels. This is a very up-to-date coal-burning boiler for use in people's homes. This is the heart of the device. Coal is fed along here by a rotating screw. It's pushed up into here. This is inside. As the coal is fed up into the cup, air is drawn in with it through these slots. The air comes in from the space around the burner. This is where the air comes in, and then through the slots. Air also passes up here and comes into the burner through slits around its rim. Here they are. The coal burns here very efficiently because of the good air supply. There's a metal surface above it to reflect heat back, so that a very high temperature is reached in this zone. The ash formed gets pushed off round the edges as fresh coal comes up to the burning zone. It falls into the ash pan at the bottom. This boiler will work continuously and automatically as long as there's coal in the hopper. And you can set the temperature you want and leave it to do the job. Another way of burning solid fuel. This is what's called a fluidized bed. Sand particles are kept floating in a current of air blown in from underneath. They're first heated up, for example using gas. If pieces of coal are now dropped in, they will ignite. They burn fiercely and evenly as they too bob around amidst the sand particles. This principle of fluidized bed combustion has been applied in large industrial boilers developed at CRE. This is one undergoing a test run. The idea of fluidized combustion was pioneered at CRE by British Coal and is now being applied worldwide. The coal is fed in from here and into the furnace. This is where the air's blown in. You can see the fluidized bed. The bright particles are the burning coal. Not only is this a very efficient way of burning coal, it can also be used to avoid pollution. Any sulfur in the burning fuel comes off as sulfur dioxide, which produces acids when it gets into the atmosphere. The trick is to stop the sulfur dioxide getting out. This can be done by introducing a supply of a basic chemical into the fluidized bed, which reacts with the SO2 to produce a harmless salt, which stops in the bed. Very, very little acid-forming gas can then get out into the flue and chimney. In the old days, coal was distilled in gasworks, and the coal gas, which was one of the products, was used as fuel in homes and in industry. Nowadays, scientists are investigating new and more efficient ways of producing fuel gases from coal. Here at CRE, there's a pilot plant for gasifying coal using fluidized bed techniques. Experimental work in laboratories, such as at the CRE, involves chemical engineering on a large scale, as you can see. It's an expensive and time-consuming business, but it's very important. All the world's fossil fuel resources, including oil and natural gas as well as coal, are precious, and we must learn to make the best possible use of them. Here's another exciting possibility, turning coal into liquid fuels, oil from coal. In this pilot plant at CRE, coal can be made to react with hydrogen under pressure, and liquid fuel is produced. The coal is first dissolved using special techniques. This is a sample of the dissolved coal. Some hasn't dissolved. It's filtered off. The solution made from coal is mixed with a specially developed catalyst and made to react with the hydrogen under pressure. It's called hydrogenation of the coal. The result is a thick black oil, not unlike naturally occurring oil. Here's the pressure vessel in which the hydrogenation takes place. The coal oil produced can be fractionally distilled and separated into useful components. Here's the distillation column. Again, experimental work on a large scale. You get a diesel fuel fraction. A fraction which can be used to make petrol, and a fraction which can be used to supply useful raw materials to the chemical industry. The solvent used on the original coal is left. This is used again to dissolve more coal and continue the process. Work like this is of great importance if the world's to make use of its natural resources. Coal is one of our most valuable raw materials. In this film, we've seen only some of the work carried out by British Coal at the Coal Research Establishment. At the CRE and in many other laboratories and industrial locations, scientists and technologists are working together to develop new ways with coal.